we already know a few things about gravity, right? We already know, in fact, long before Isaac Newton, Galileo figured out that objects of different masses fall toward Earth at the same rate. They accelerate toward Earth on average at 9.8 meters per second squared. So, for an object near Earth's surface, we already know the acceleration due to gravity does not depend on the object's mass. The force, which is the weight of the object, does depend on the object's mass. So, if we look at planets moving around the sun, we can expect something similar. The question was asked previously, what's missing from this inverse square law? We saw proportionality. The proportionality statement said that force is proportional to the mass of the central object over r squared. Well, we're missing two things actually. To make this an equality, we would have to add the mass of the second object, m2, and we would have to add some kind of a constant, the gravitational constant. So this is the equation. This is called Newton's law of universal gravitation. Isaac Newton figured out that the force of attraction between a central body and an orbiting body, the force is equal to g times m1 times m2, the mass of the first body times the mass of the second body, divided by r squared. So this is an inverse square law, and we do have a constant there that makes this an equality. Quite often when we have a proportionality and we want to figure out what the equality is, we need to figure out what is that number that we need to multiply one side of the equation by to get it to equal the other side of the equation. And so quite often we have constants. On the previous, on that graph of Kepler's third law, we had a different constant for each central body, which was k, lowercase k. For Newton's law of universal gravitation, it is always capital G, times m1 and m2 over r squared. So we have that constant, and we need to know what that constant is in order to be able to calculate gravity, and we will get to that very soon.